make sure that I pronounce your name correctly. It's Xavier Puig. It's very beautiful. It sounds like a poem, Xavier Puig. Where are you from? What is the origin of the name?
I'm from Barcelona, so it's a Catalan name.
Nice.
But
Awesome.
depending, even within the region where I live, they like pronounce it differently depending on the region. So it always causes like a lot of confusion.
Yeah, I can imagine. Xavier Puig. Okay.
So yeah, today I'm going to talk about Habitat 3.0, which is a simulator to train robots, humanoid avatars, and to study social human-robot interaction tasks. And this is work done jointly with my group at FAIR called Social Intelligent Robots. And our goal is to build robots that can assist humans at everyday tasks. And so what this means is that we want to have robots that can navigate in indoor environments while humans are doing activities in them, that can interact with different objects and manipulate them around to do different tasks, but that can also interact with humans, that can understand what are their goals, their intentions, that can adapt to their preferences, and that can do tasks together with them in an efficient way and safe. And this comes with a number of challenges. First, we want to train robots that can generalize to a wide range of tasks and also environments. And so we know that this requires us to have access to data that represents this diversity of tasks and environments. But when we test robots on the real world, we generally are limited to relatively constrained scenarios and a limited set of tasks. The second challenge is that we know from past experience that in order to train robot policies robustly, we need to have access to large amounts of interaction data so that robots can learn with. And so this means that we need to be able to find ways to efficiently gather this data so that robots can learn to perform interactions in the environment, but also do it in a safe manner because these robots will have to be interacting with real humans. And the third challenge is that we don't want robots to only be able to adapt to a wide range of tasks and environments, but because they're interacting with humans, we need them to be able to also adapt to different kinds of humans, adapt to their behaviors, follow their preferences, and also adapt to the way they prefer to do different kinds of tasks. And so one approach that has shown some success in addressing some of these scenarios has been to leverage simulation technologies to very efficiently gather interaction data across a wide range of environments. And in fact, multiple research groups have actually been pushing in this direction, both developing different kinds of simulators to gather interaction data with which to train agents, and also training these agents in these simulators to do different tasks like navigating in indoor and outdoor scenarios, interacting with objects, and so on, and showing that these agents trained in simulation could later be deployed in the real world. And in fact, my group in particular has been focusing over the past years on really pushing for developing this kind of simulators, in particular Habitat, the simulators you see in the left, which enable like very fast interaction, and also training robot policies to navigate in environments in these simulators and also interact with objects so that they would be deployed later in the real world. And in fact, we have managed to have some success in this area, training policies that would, again, navigate to different areas and also interact with objects and deploy them in the real world without any real world like post-training. And so what I'm going to show you here is one demo where we train separate skills and connect them with a large language model that will convert a task descriptions into a set of skills that the robot can execute. And so what you see here is that given a task that describes about like growing a chocolate box and putting it on the table, we can execute a policy that was trained purely in simulation and in an environment that was never like in other kinds of environments and be deployed in a real robot. And so what is impressive here is that this robot has never seen this apartment. It has never been trained in the real world, but it's still able to execute this action. This is great. We can like command robots with language to different kinds of tasks. I would argue that we're really not doing human-robot interaction here. Like the human, as you saw, was in one corner of the room instructing the robot, but the robot was really not interacting with the human in an active way. And I would argue that if we want to have robots that have these kind of behaviors, we need to put charge simulators with human models so that robots can learn to not only interact in environments, but also interact with humans. And so it's true that some of the simulators that I presented above have done some progress on representing these humanoid representations, but generally they are like not efficient enough or they don't include robots, which makes them not fit to train robot behaviors to interact with humans. And so it's for this reason that we developed Habitat 3.0, which is a simulator that is designed to represent very efficiently both robots and humans in a wide range of environments and train robots to do this kind of like collaborative tasks. And so there are like three key features that I think make Habitat 3.0 a good simulator to develop these human-robot interaction skills. First, because it builds on top of the Habitat platform, it allows to have very, very fast interaction, and so an ability to very quickly collect interaction data, and also access to a wide range of environments. The second thing is that we include realistic and very efficient humanoid representation that will allow us to train robots with these humans. And I will go over that in a moment. And the third thing is that because we want real humans to interact with these robots, it provides tools that allow real people to interact with these robots and see how they behave, even though they were trained in simulation. So to represent humanoids, what we do is we take a simple X, which is a body model that allows us to go from a set of like sparse human joints into this mesh that represents a full human. And so Simple X is a model that is trained on a big data set of real human scans, and it allows to very efficiently represent different kinds of genders, body shapes in a realistic manner. And so this has two advantages. One, it gives us a very easy way to represent realistic body shapes of different shapes and genders. But also because it is a body representation that is very widely used in computer graphics research, it allows us to leverage a lot of this research in our simulator. And so what I'm showing here is some motions that are not authored by an artist, but actually come from a neural network model that takes as input text and outputs motions. So that means that we can very easily generate realistic human motions in the simulator that will allow us to train better robots, but it also allows us for the computer graphics community to use the simulator to study these kind of problems. Okay, so we have a body model that allows us to represent real humanoids in simulator and potentially different kinds of motions. But what we really want to do is to equip this human model with behaviors that will be relevant once we train these robot tasks. And so what we did in this work was to take this body model, adapt it to our simulator, and design a set of like primitive actions that would allow humans to have complex behaviors. And so we cared about humans that could navigate in environments and also interact with different objects. How do we make humans navigate in these environments? We take a clip of motion capture data, which means somebody that went to a body scanner and recorded themselves like walking in the environment, as you can see here. We took this clip, and what we do to make people walk in different scenarios is to play this clip in a loop and retarget it to different paths, so that if we want a human to walk in an arbitrary path in an environment, we will just be retargeting this motion so that they have like a realistic walking behavior. We also want humans that are able to realistically interact with different objects in the environment and like exhibit realistic motions. And for that, what we did was to take an existing model trained to generate realistic poses that followed some constraints. In this case, the constraint that one of the hands should be reaching a position. We use this model to generate offline a bunch of like these like poses of people reaching different spaces in the environment. And then during simulation time, if we wanted a person to exhibit these reaching behaviors, we would query this offline data set of generated motions and interpolate over it to have this realistic reaching behavior. And so what this allows us to do is to basically have a simulator that can represent both robots and humanoids interacting in the environment, moving around and interact and manipulating objects to represent realistic like and diverse tasks. Okay, so Habitat 3.0 provides us a platform that enables fast interaction in a wide range of environments and humans, where we can train these robots that later will be deployed in the real world. However, as you can see, there's like significant differences between the simulated domain and the real world domain. And so that means that policies that we train in simulation may not be working exactly as we expected in the real world. This is a problem that is well known and to some extent has been addressed. But one challenge here is that we have two sources of domain gap. On one hand, we have the environmental domain gap, in which we had a simulated environment, and now we have to deploy in a real environment with physics and more complexity. And on the second hand, we have the human domain gap, in which for the first time we're training robots with simulated humanoids, but we will need them to interact with real humans in the real world. And so this is extra challenging in our case because we need these policies to actively interact with humans. So we need to make sure that they do them not only effectively, but actually safely, because they will be interacting with humans. And so it's for this reason that what we did was to build a human-in-the-loop interaction tool that would allow real humans to interact in the simulator with robot policies. And so this tool in particular allowed people to control with mouse or keyboard a humanoid to interact with this robot, or also with virtual reality. And so this will allow us to test whether these robots that we train in simulation are actually effective at interacting with real humans. So far, we have a simulator that allows us to represent robots and humanoids and tools to test these robot policies along with real humans. Now we want to see if this simulator will allow us to train robots to do useful human-robot interaction tasks along with humans. And so we thought about two tasks that represent interesting challenges in human-robot interaction scenarios. The first one is we call it social navigation. And the goal here will be to have a robot that can find a human in an environment and follow them around as they move around the environment. And so you can imagine that this is useful if you want to have like a video call around the house and you want the robot maybe to follow you to keep track of your camera, or you want a robot that makes sure that you're not falling on the floor, or you just want them to understand what you're trying to do so that they can help you effectively. The second task, called social rearrangement, will evaluate whether a robot and a human can collaborate effectively in rearranging objects in the scene. And so you can imagine that this is useful if you want to, for instance, to clean a house together with a robot. Let me talk first about the social navigation task. So in this task, we will have like one environment. We will have like one of the humanoids, a robot that will be placed in different rooms in the environment. And we'll start by designing, by using the planner that I defined before, to have the human like walking around the environment in a random fashion. So we will be selecting a random point in the environment and walking around it. The robot will first have to navigate to find the human as efficiently as possible, as quickly as possible. And once it has found the human, it will have to follow the human without colliding with them. And so what it means here by follow is that we want to, basically the robot has a camera, you want to keep the human in view as the human is walking around the environment. And so we will measure 3 metrics to measure like what is the effectiveness of this task. We'll measure how quickly the robot is at finding the human in the task, in the environment. We'll measure for how long of the task the robot is effectively following the human. And finally, we will measure whether the robot is following the human safely. And so what is the rate of collisions that the robot does with the human. And so the robot here, a robot agent, will have 2 possible actions, one that allows it to move forward and one that allows it to rotate, like basically do some like angular velocity. And it will have access to 3 sensors. A depth sensor that will be mounted on a camera on the robot, a humanoid detection sensor, which just takes the depth sensor and masks out the like humanoid area. And finally, a humanoid compass that tells what is the relative position between the robot and the human. And so you may think that the humanoid compass makes the task trivial because we know what is the orientation of the robot and the human, but notice that the robot has never seen the environment that I showed before. So it still needs to learn to navigate around a space that it hasn't mapped and find this like moving target, which is the human. And so we'll consider 2 main baselines. Oracle heuristic, that basically where the robot is equipped with a path planner that allows it to navigate perfectly to different locations in the environment. But the robot still has to follow the human. So as soon as it finds a human, it will be making sure that it's within some distance. And a learning-based baseline where we'll have the robot trained with reinforcement learning. It will only take as input this depth sensor, the humanoid detection, and the compass. And it will be taking, like this policy will be taking as input these velocity actions to follow the human effectively around the house. And so if we look at the metrics that I was describing before, of course, the path planning Oracle baseline, it's much more efficient at finding the human. It's still not perfectly efficient. I can describe like on the Q&A, why is that? Like we have like one baseline that maybe it's like more optimal, but it's like pretty good at finding the human. When we look at how good is at following the human or colliding with or not colliding with the human, we actually see that the reinforcement learning baseline and the planning baseline are actually very competitive with each other. And so the reinforcement learning baseline is able to locate the human. It has like a very reasonable success and then find the human effectively. We also measure how a reinforcement learning baseline would work if we just remove each one of the sensors I described. And so obviously, if we remove the compass, the human compass sensor, it will take much more for the robot to find the human, as you can see on the plot here, but it still can follow the human pretty well. On the other hand, if we remove the depth sensor, I don't know if you can see my mouse, but you can see on the plot on the right that when we remove the depth sensor, the robot is like colliding much more with the human. And so what I'm going to show here is a visualization of how the reinforcement learning policy with all the sensors looks like. On the left, you will see the human walking around the environment, and on the right, this robot policy trained with RL. And so as you can see, without having like knowledge of the environment, the robot is able to avoid walls and start following the human around the environment, and also rotating to keep it in track. And so you can see something interesting, which is that an emergent behavior emerges in which the robot learns to not only follow the human, but also backtrack when the human is rotating to avoid colliding with the human. And so the robot is not only keeping track of the human, but actually letting it do like its navigation effectively. Okay, so I talk about social navigation, which is only about robots following the humans. but we want robots to actually be able to interact in a house along with humans and interact effectively. So in this second task, what we measured was whether two robots can manipulate, rearrange objects in an environment together. And so similar as before, we will have a human and a robot in a task. We will have two objects that need to be rearranged and also to target places where these objects need to be placed. And the task will be for the human and the robot to rearrange these two objects as efficiently as possible. One catch here is that we want a robot to not only be able to rearrange these objects effectively in the environment, but we want to do it effectively with many different kinds of humans. So one property that we care about here is that the robot can adapt to different kinds of human behaviors and still do this like effectively. And I will explain in a bit how we represent these different human behaviors. And so we will evaluate two metrics to measure how well is the robot at doing these tasks. First, we will measure the success rate. So whether the robot and the human can pick and place these two objects effectively in the scene. And second, we'll measure how efficient they are at doing that. And so for that, we will basically measure what is the time that it takes for the human alone to do the task versus for the robot to do the task in the environment. And so because this task is more challenging than before, because you need to be able to reason with different objects and manipulate those, we will basically design a set of high-level skills that the robot and the human will be able to call in the policy. And so the robot and the robot will still be a reinforcement learning-based policy, but instead of calling this forward and backward velocity, it will be calling these high-level skills to interact in the environment. And so in particular, it will be able to navigate to either the target objects in the scene or the target receptacles. It will be able to pick these objects, place the objects in a receptacle, and also at some points it will be allowed to move either either forward or sideways to avoid colliding with the human. And so here, similar as before, the robot has a depth sensor and a compass sensor of where it is relative to the human, but we will also be measuring where the robot is relative to the target location and the two target objects. We have a robot that has to rearrange objects with different kinds of humans. And so how can we train this robot effectively? So the first thing that we can do is we want to train them with reinforcement learning. The first thing that we can do is to train them with another policy for the human, where we will be training the two policies together to rearrange objects in the environment. And we can just give a reward for when the objects are picked or placed into different parts of the environment. And so what you expect from these policies is that each one of the policies will learn to perfectly coordinate because they jointly want to get as quickly as possible at doing this task. And so what you imagine that will happen here is that one of the policies will specialize in picking one of the objects, and the other policy will specialize in picking the other object. The problem here is that when this robot is partnering with this human, it will be as efficient as possible. But as soon as you partner it with a different kind of human, these assumptions will break. And if the human is trying to pick the same object that the robot was trying to do, this will fail. And so to address this, we take inspiration from the zero-shot coordination literature, and we will train a robot policy to be robust to many different kind of human policies in this scenario. And so the goal here is to have a robot that not only specializes in one object, but can do behavior that adapts to all those. And so for that, the setting is pretty similar as before, where we have a policy that we'll be using to train the robot. But for the human, instead of using a policy, we'll be sampling a set of policies. And so on every episode, we will be taking one of these neural networks. We will be training the robot and the human network during some iterations. And later we will be taking another neural network for the human. And so the idea is because the neural network for the robot is always the same, these models should be able to adapt to these different kinds of humans. We know from cognitive science literature that humans many times behave as Boltzmann rational agents, which means that they are if they have a clear sense of their goals, they can act according to their plans. And so because of that, we wanted to test also how robots would perform when they are paired not with a neural network of a human, but with an actual planner. That given some goal, for instance, putting an object in a given container, know exactly what are the sequence of actions that should be taken to do this action. And so we consider 4 kinds of planners for the human. One planner is, the first planner is the most constrained one, and it's one where the human will always be rearranging the same object in the environment. And so you can imagine that similar to the learning single baseline that I described before, the robot should generally specialize on rearranging the other object. And so this should be very efficient when it pairs with this human. The second planning baseline, we assume that the human will either choose to rearrange the first object or the second object in the environment, which means that the robot has to anticipate which is the object that the human will rearrange and rearrange the other one to do the task effectively. We will also consider what happens when the human can either rearrange one of the 2 objects or both objects. and in which case the robot should learn to stay in place to avoid obstructing the human or colliding with them when doing the task. And finally, what happens when the human can do anything? It can rearrange 1, 2 objects, or can just stay in place. And so in this case, the robot has to learn to, when the human is not moving, rearrange the 2 objects in the environment. And so if we look at the success rate of these baselines that I described before, as I said before, like the baseline where the robot is trained with a single human policy is the one that gets the best success rate because they have specialized to do each one of the tasks. Somewhat surprisingly, it performs better than the one where you have a planning human that only does one of the tasks. And my theory is that it's doing that because the human policy maybe learns to get the object that is closest to them, whereas the planner doesn't reason about that, and that lets them to do the task like more efficiently within a budget. Learning single is the best baseline, but what happens when we pair all these baselines with different kinds of humans? And the way we will model these different kinds of humans will be by taking a small sample of each one of the humans that I described before and pairing each one of the baselines with these samples. And so obviously the results become much worse because these robots were not trained to interact with these humans, but that's really what we want. We want robots to be able to adapt to many different kinds of humans. As I was explaining before, obviously the policy that was trained with a single human lowers a lot in performance, and the model that ends up working the best in our experience is the one that is trained with a human that can either pick 1 or 2 objects in the environment. 2 questions emerge from this. One is, why is not the robot generalizing better to an object that could pick, to a human that could pick also none of the objects? And I think the reason is because if the human doesn't pick any of the objects, then it's more work for the robot and it's harder to learn. And the second question is, why didn't the population-based training baseline that I described before doesn't work better than the single one? So I think that this actually is probably due to undertraining. And so I would expect that with more training iterations, this population-based training to be able to perform better. We also measure whether these baselines are not only successful at executing the task, but can also do it efficiently together with a human. You can see that there's here, this metric basically will be 100% if it takes for the 2 of the agents the same time as the single agent to do the task. Somewhat good news, there is some improvement, so the 2 agents can help, a robot can help the human do the task more effectively, but the improvements are relatively low compared to what we could do. And so what we saw is that the reason why this is happening is because in many cases, the robot has to back up to let the human do actions. And so there's many of these cases where the 2 actually cannot do anything because they're in front of each other. And so this is challenging because the robot has to coordinate, but also leave space for the human to do these kind of tasks. And so here I'm showing an example of this collaboration task, where in the left, you will see the human rearranging objects, and on the right, you will see the robot. You will see that the robot, basically the 2 policies learn to specialize in picking different kinds of objects. This is the baseline that is what's working best. And so each one of them picks one of the objects and then places them on the different containers. Robots can adapt to simulated humans in simulation. But the next question is, how does this help us in building robots that really can help real humans interacting in these environments? And so what we wondered is, okay, can these robots that were trained purely in simulation assist real humans in the environment? And what we did to test that was to adapt this human-in-the-loop interface that I described before to represent this social rearrangement task. And so you will have a task where a human will be given, will be tasked with rearranging these 2 objects in the environment. And you can see how whenever it picks an object, it basically there's an indicator of where it should be placing it. And it will be paired with different of the robot baselines that I described before. So you can see here, the robot also rearranging objects in the task. And so we will measure whether the robot paired with the human can do the task again effectively and with a reduced amount of time. And so we did a test with 30 participants in our study, where every participant would either do the task alone or the learn single baseline. This is the baseline where the robot was paired with a single human policy, or a planner baseline, the one that was working best. And so it's nice to see that the human, these are the performances with the simulated human. When we pair them with the real human, the performance actually improves. So the robot can actually help the human do the task more efficiently than the robot alone. And so you can see here actually that the results are a bit different than what we saw in simulation. So here, the baseline that was trained with a single human is performing better than the other one. The reason why this is happening is because the blue baseline has a lot of variance. So when it pairs with a human that focuses on the right object, the 2 agents will do the task super efficiently. but as soon as they pair with a human that does differently, they will do very badly. So despite these variants, because the success scenarios are so successful, this leads to better efficiency for the robot. To conclude this talk, in this talk, I introduced Habitat 3.0, which is a simulator to represent humanoids and robots in indoor scenes, and which enables to train these robots at scale in a large set of environments. I presented 2 collaboration tasks to show that robots could actually be trained in simulation to coordinate with different humans, in particular social navigation and social rearrangement. And I showed that these policies not only learn to coordinate with humans, but actually learn emergent behaviors that they were not trained for. Like in particular, the robot learns to avoid the human in some cases, and also coordinate with like novel kinds of humans. And I finally showed that we can like train these robots in simulation, test them with real humans still in simulated environments, and actually have these robots actually being efficient when partnering with real humans. But the question is, like, our goal really is to have robots that can assist humans in real world scenarios. And so how do we go from all these results to having robots that really are helpful in physical scenes? And so we have seen over the past year with like the use of LLMs, how offline data can actually be very useful at training robot behaviors to do complex plan in physical scenarios. But despite this progress, I would argue that simulation environments will still play a key role in developing robots that can collaborate with humans. Why? Because these language models will need to be grounded in environments so they can coordinate with humans effectively. And also because many of these tasks will involve humans in them, we need ways to test these scenarios safely. And we need to come up with adversarial scenarios to test what are the breaking points of our policies. There is some work that we need to be doing on the simulator side to leverage that. So something I'm very excited about is how can we combine language models and data sets of human behavior to make more realistic humanoid models in simulation so that we can train these robot policies to do a wide range of tasks.
Is it like the sort of next step in your research, like combining the LLMs?
Yes, we are looking into that now. So how like I presented like a reinforcement learning policies that would represent the humans together with those abstractions. Our next step is how can we use LLMs and data sets of human behavior to build more realistic human behaviors. With that, I would like to conclude my talk by thanking my amazing collaborators. This was like a huge effort, and it will be possible with them. And thanking you all for coming. I'm happy to take questions.
Awesome. Thanks a lot for your talk.